In this lesson, you're going to learn how to graph polynomials. So let's examine this cubic polynomial. What points would help you graph this by hand? Hopefully you're observing that there are 1, 2, 3 zeros as we would expect. So knowing those 3 zeros would help you graph. But additionally, these 2 gray points, this one here and this one here, will help you make an accurate sketch. So in order to graph polynomials of higher degree, you need to find these 2 main things. You need to find the zeros, which we spent an entire unit working on, and any extrema. So let's define extrema. So in order to graph polynomials of higher degree, you need to find the zeros and any extrema. And the extrema would be those 2 points that I highlighted in the last function. There are 2 types of extrema. There's absolute and local extrema. Local extrema is also called relative extrema. Okay, to understand this, let me sketch a picture of a polynomial function. And sometimes I say, if you think of this like a roller coaster, there's some important points on this roller coaster. The places where it changes direction, like we have this little hill, and then we have a valley, and then we have a higher hill where you put your hands up. Right? These green points that I just labeled, these are your extrema. They are, 2 of these are local and 1 of them is absolute. So this right here, the top of this first hill, that's the maximum height in that general area that you're going to reach. So this is known as a local maximum. Okay? You're going to get higher than that on the roller coaster over here. You're never going to get higher than this point right here. It's the absolute maximum value that you're going to reach. Whereas this one right here is a minimum value. Now, it's not the absolute minimum because if you see these arrows, this function goes forever down. So you're never going to have an absolute minimum because it's going to keep going and going and going. But this one right here is a relative or a local minimum. It's a minimum value in that general area. So I think of extrema as the hills and valleys on a roller coaster. It is possible that you have no absolute extrema in a polynomial function. If you had one that looked like this value here would be a local maximum because you will get higher than that, so it's not an absolute. And this one right here would be a local minimum because, again, you'll get lower than that. Another key idea you'll be asked about is what is the maximum number of turning points the function has? So let's consider several functions that you're familiar with. A linear function, y equals x. You know that that is a line straight through the origin for the parent function, and it doesn't change direction at all. It has 0 turning points. That's what I mean by turning points. How many times does it change the direction versus up or down? So let's look at a quadratic, y equals x to the 2nd power. In general, it's a curve, it comes down, changes direction, and goes back up. How many times does it change direction? Well, just once. Even if it were upside down, if it were a negative leading coefficient, and it was like this, it would be going uphill, changes direction, goes back down. So 1 turning point. Whereas y equals x to the 3rd, you may not be as familiar with that one, but that looks something like this. Goes uphill, changes direction, back down, like this. So how many times does this change direction? It's twice. So what pattern do we see? If you compare the number of turning points with the degree of the function, how do these values compare? 1 to 0, 2 to 1, 3 to 2. Hopefully you're observing that if I have a polynomial of nth degree, the number of turning points is n minus 1, or I should say the maximum number of turning points. It is possible to have a function that doesn't have quite that many turning points, but that's the maximum. For instance, if I asked you y equals x to the 4th, we would expect it to change direction 3 times. But you will see some where it only changes direction 1 time, where it looks wider like this. But the maximum number of turning points would be 3. Okay. The last general thing that will help you make sketches is if you understand the general shape of all polynomial functions, and let's start with one you know. So odd functions. An odd function would be y equals x to the 1st. Well, that's linear. You are very familiar with linear functions. They look like this. Whereas if it was y equals negative x to the first, well, that has a negative slope, so it's going downhill. Every other odd function looks somewhat like this. Here's what I mean. If I have y equals x to the third or y equals x to the fifth, in general, out here on the tail ends, the function's going to look the same. It's going to go in the same general direction. It's just going to turn around a few times in the middle. So x to the third, it's going to come down. It might wiggle around here and back up. X to the fifth is probably going to have more turning points. It's going to change a couple of times in here and then go back up. But as you see, these ends, which you'll learn in a future lesson is known as the end behavior, will all look the same. Whereas if the leading coefficient is negative, it's going to look like this one above here, like this. But if it's to the third, it's going to wiggle around here in the middle. If it's to the fifth, it's probably going to turn around more times here in the middle. So let's talk about the general shape of even functions. Let's start again with one that you know very well, y equals x squared. You know that that is a parabola that looks like this. Whereas if the leading coefficient is negative, it opens upside down. It looks like this. Okay, so in general, anything that's even, like x to the fourth, out on the edges here, it's going to look the same. It's just going to turn around more times in the middle. So in general, it's probably going to look something like this. It could move around here in the middle, but the edges go up the same way a parabola does. Whereas if the leading coefficient is negative, it's going to kind of look the same, but wiggle around in the middle. Okay, so let's put this all into practice now, and we're going to use technology to help us graph this function. So this first one, y equals the quantity x minus 2 quantity squared times x plus 1. First of all, I know that this is a cubic function. How do I know that? Well, right here, this is going to produce an x to the squared, and I have another x right here. Overall is going to give me a cubic function, x to the third. And my leading coefficient is going to be positive. So I know it's odd. It's going to look something like this. It's going to wiggle around in the middle, but it'll look like that once I'm done graphing it. Okay, so let's start with the maximum number of terms it could have. N minus 1, it could have 2 turns. What are the zeros? Well, since this is factored, I know that there is a 0 at x equals positive 2. It's opposite of the factor. It has multiplicity 2, so there's going to be another one there, 2, and 1 at negative 1. Now, I'm going to actually graph this on Desmos, and since you're at home without graphing calculators, I would suggest that you use desmos.com, which I have linked on Schoology, to practice this. So to graph the polynomial in Desmos, you just type your function over here and it automatically draws the curve. And the beautiful thing is if you just click on these points, it tells you the zeros. Here they are, -1, 0, and 2, 0. You can see the graph bounces off like we expected. And up here is a local maximum. It's not the absolute because it goes higher, but this is a local at 0, 4. The graph also has a local minimum. Okay, so think your peaks and your valleys. The local minimum occurs right here at the ordered pair 2, 0. Now the imaginary zeros that it has, the first question that I bypassed, well, we know that the function is cubic, so altogether it has to have 3 zeros, a combination of real and imaginary. Well, since I have 3 real zeros that I can see, that means there are none left over to be imaginary, so I have 0 imaginary zeros. The domain and range, so how far left versus how far right. Well, this graph goes forever left and forever right, so it's going to be all real numbers. And the range, forever down and forever up, so all real numbers for this one. All right, this next one is also a cubic function, so I know I'm going to have 3 zeros altogether. As far as what does the general shape look like? Well, the leading coefficient's negative, so think negative slope. It's going to be like a line, but wiggling around in the middle a little bit, so something like this. All right, so go to Desmos and actually graph this function. Okay, so I've graphed this function, and let's answer how many imaginary zeros does this have? Well, I can physically see 1 0. So if it has 1 0, I know it has to have 3 total, so that means there are 2 imaginary ones that I can't see. What's the maximum number of turns it has? Well, it's got to be 1 less, so 1 less than 3 is 2. And where is it turning? Well, it's going downhill, turns here, goes uphill, turns again right there. All right, the zeros, what do I actually see? And I should say the real zeros. The real zeros, it crosses at negative 0.9. I'm going to round to the nearest tenth rather than negative 0.891. So negative 0.9. The extrema. So again, I don't have any absolute max or absolute min because it goes forever up and ever down, but I have local max and a local min. So my peaks and valleys. Local max and local min. So my local maximum, the peak, occurs at this ordered pair, and I'm going to round it to the nearest tenth again, so 0.7 and negative 2.7. My local min is also the y-intercept right there, 0, negative 3. All right, let's state domain. Again, forever left and forever right on this one, and the range is the same, goes forever down and forever up. Okay, in this third example, this one is quartic. It's to the 4th power. So my leading coefficient's positive, so even ones think they look like parabolas kind of, but turning around in the middle more. So the edges like this, but it's probably going to turn a little bit. Overall, it's going to look something like that. All right, so switch to Desmos and graph it. So the number of imaginary zeros. Well, I can see 2 real zeros where I can physically see it crossing, so that means the other 2 must be imaginary. Okay, just remember that imaginary ones always come in pairs as well. The maximum number of turns, it can change direction 3 times, 1 less than the degree. What are the zeros I see? I physically see it crossing at 1.3 and 2.8. The other 2 would be imaginary. Now, the extrema. Now, it's definitely, I've got a valley right here. This one right here, sometimes kids want to call this a peak, but it's changing. This one's actually known as an inflection point. You don't need to know that for me, but it does not actually dip there. It just kind of, it's like this. It's just downhill. It's kind of a squiggle, but it's not actually a peak. Okay, so this one down here is an absolute minimum, okay, because the graph never ever gets lower than that point. So 2.3 comma negative 4.5. I'm just being consistent with my rounding. I'm going to the nearest tenth. My domain. So this time, forever left and forever right. So it is all real numbers for my domain. My range, however, is what's the lowest it goes? Well, it's this y value right here, and then it goes forever higher. So this would be y is greater than or equal to negative 4.5. Again, just rounding to the nearest tenth. Okay, so that's an overview on graphing polynomial functions with the aid of technology. Please reach out if you have any questions. Make sure you do the practice to really understand this.